You guys just joining us, I apologize. We were grading a little bit before we started recording. So go ahead and pause the video right here and you can grade the beginning evens. I know there are some odds too. I did give a quick little hint, since we do have that quest tomorrow, about symmetry. Remember, whenever we have a function, a polar function in terms of cosine, it will always have polar axis symmetry. That's something you can study and not have to do all the plugging in, all the tricks. Same thing over here. When we have this guy that only has a sine, whenever you have a polar curve only with sine, you will always have pi over 2 symmetry. That's something you can study. It's in our notes. It's a trick. There are other ways of doing it, but one way is the trick of, does it have cosines, does it have sines? Now, if it had both, we might be in some trouble. But, bless you, bless you. We also talked about how to solve something like this, because we are not just finding the maximum, but also finding when it occurs. And for the zeros, we also have to figure out when the zeros occur. So we're setting functions equal to values and then having to solve. And we reminded ourselves really quickly that to undo sine, we need to do sine, bless you, inverse. I've been sneezing this morning too. Allergies, huh? Sine inverse says, when does sine equal? So I showed the little in-between step over here off to the side of when sine equals 0 at 0 pi, 2 pi, 3 pi, or up here, when does sine equal plus or minus 1 at pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. And I think it was Tony that was helping me out as far as we need to multiply by 1/2 to get rid of. Need to multiply by 1/2. Down here, we also need to multiply by 1/2 to get the theta all by itself. So that's just solving, and that's how they got their final answers that you guys are able to see here as you're grading, and then here as you're grading. We talked about how in the quiz tomorrow, or for the quest tomorrow, you're going to be listening very carefully as to whether or not, or what I say about you using calculators, but the unit circle will still be important. But it's also important to be able to make a table, and from a table, a polar curve, whether or not you're using your calculator. Whether it's one of these guys where you get a rose, one of these guys where you get a limaçon, it's also important to know the names. Now, a big part of tomorrow will not be just matching equations with names. That's not tons of points. But knowing how to name what you see is important as far as a limaçon, or as far as a cardioid, or as far as a rose, or as far as a dimpled... Oh, is that it? Are we done? Oh. Isn't there a dimpled? Is there a dimpled one in any of these? Oh, there isn't. There's a lemniscate. They don't go with a dimpled one. They just say a limaçon. Anyway. I think that's good. How was your guys' calculator for number 54 and 62? Did you get it okay? Did you realize that number 62, 0 to 2 pi wasn't enough? You had to extend your window. So remember, when you hit the window button, you now have in this polar, for parametric, you have T-min and T-max. And you can make T-max go farther in order to include more of the graph. And for polar, you have theta-min and theta-max, and you can extend or expand or put in a higher number for theta-max to have it go further. So 2 pi would have only gotten you half of that graph. You had to go all the way to 4 pi to get the whole thing. Any other questions about calculator or polar curves or the homework last night? Yeah, Gavin. Okay. My first direction to my honors pre-cal kids would say, look and ask yourself, is it a function in terms of sine? Is it a function in terms of cosine? If it's in terms of sine, I would say memorize. It's going to have pi over 2 symmetry. Okay? So whatever's on one side is going to be just a very helpful trick, a very helpful clue. And if it has cosine instead, it's going to have polar axis symmetry. It kind of has to do with, if this helps at all, if you know the unit circle. Why pi over 2 and why polar? Pi over 2 is the y-axis, polar is the x-axis. Sine goes with pi over 2 because sine in the first quadrant and sine in the second quadrant are the exact same values. So at pi over 6, sine is 1/2. At 5 pi over 6, sine is 1/2. In the first and second quadrant, sine is the same. That's basically why this is going to work. And for cosine, he's the same in the first and in the fourth. So that's a silly way of remembering it, but it does help a lot because the homework ones that you guys saw, the evens at least, you just needed to know, oh, it's a sine in there? Sweet. Pi over 2 symmetry. It's a cosine in there? Sweet. Polar axis symmetry. But Gavin, as soon as we go outside the ones with sines and cosines, like the examples we saw yesterday, no sine, cosine, no sine, cosine, that's when using your points and plugging in is going to be helpful. And so we can peek back really quickly at what the book did as far as solving for symmetry. But the long story short is, if it has pi over 2 symmetry, you can plug in this point and simplify. And you get an equivalent expression is what the book says, or you end up simplifying to make it look the same. If you can simplify after plugging in to make it look the same, then it will have this symmetry. If you can simplify after plugging this in to make it look the same, it will have polar axis symmetry. And if you can simplify after plugging this guy in, it's the same, it'll have pole symmetry. Now up here when we plugged in any of these three, we ended up, even after like moving negatives and multiplying and dividing, it wasn't matching. So none of these symmetries worked for that guy. He had absolutely none. But this guy, when we went to plug in the pole axis, even though the first two hadn't worked, the pole axis, when you plug in a negative r squared, it ended up simplifying to be positive r squared. It stayed the same. And plugging in a positive theta stayed the same. So when you plugged in this point, it stayed the same. It had that symmetry. So that's how the points work. If you plug in and simplify and it stays the same, it has that symmetry. Okay. Now they went ahead and did that with, what was it, the cosine one, I think? Where is it? Yeah, see, they were plugging in like negative r, negative theta. They were plugging in r, negative theta, and plugging in negative r theta. But the problem is with the trig ones, you have to remember even odd properties. Does it stay the same? Does it switch? I think it's so much easier just to memorize. Cosine goes with polar, and sine goes with pi. Yeah, that's totally fine. Any other questions on homework 10.8? Kyle. Oh, sorry, Johan, go ahead. Sine and cosine don't have pole symmetry. The lemniscate does. This little guy, where is he? He has pole symmetry, but I don't think anyone else. Does anyone else have pole symmetry? Oh, some of the roses might. Like this one would have pole symmetry. What's here is here. Or that one would have pole symmetry. So if we were to look at these guys, the crazy thing on this one is he has a cosine. So we would say he has polar axis, and it's true. We're not wrong. The problem is he doesn't just have polar axis. He also has pi over 2, and he also has pole symmetry. Because there's no addition or subtraction and with this little cosine guy, it's hard to even explain why. Going through and plugging in. The long story short is those 3 points that you plug in, when you plug in to something like this form or this form, all 3 are going to work. That's the long story short. But if you notice the difference between this and this one, well, what's the difference? Like, I don't get it. This one only has polar axis, and this one has polar and pi over 2 and pole. It's all to do with how many petals. So you could, once again, you could plug in those 3 points. Only one of them will work in this one, and it'll only be the polar axis. All 3 will work in this one. Or, from what I just said, you could say, okay, whenever I have a rose, whenever I have like a 2 theta, 3 theta, 4 theta, if it's an even number, I know it has all the symmetries. If it's odd, it only has. So you could add like a little bit of sine and cosine and not have to plug in all 3. But that's just more of a if n is even for roses. all symmetries. The other one that I just looked at, the lemniscate, he also has pull. If we go look at him, let's see, all symmetries. Oh man, I can't spell symmetries. La. Bleep, 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 bleep. Okay. If n is even, all symmetries, and this guy, n is also even, right? So that's a quick little add-on. If n is even with roses, it's going to have all symmetries. Or you could plug in all your points. They would all work. But the lemniscate, is a little bit different in the sense of he's not r equals with one function. He's r squared. So he's just a little bit complicated in the sense of he's not just in terms of sign. So yeah, that's the hard part, and that's why the book probably doesn't, I mean, it does, because I think I stole this little box out of the book. I talked about it first. It does list this, and it's a quick test, but there are some exceptions. And the exceptions come with roses and lemniscates. Lemniscates are the weird r squared ones, and roses are the n theta ones. So that was good, Johan. That was a good question. There are some exceptions, which makes it a really good one and a really fast one. But there are some exceptions that can trip you up if you don't know what the shape of the graph looks like. The safe way is to plug in all 3 points. It's just nasty, and I don't like it if I can avoid it. So that's why I try to show you guys the quick test. Kyle, what was your question? Secants and cosecants. Can we peek at it real fast? Number 43? Were there any other ones in homework, guys, that were like, oh, that was nasty, that was gross, not cool? You were trying to sketch and do all the nasty. No, Kyle, I won't give you one with secants or cosecants or like nasty extra forms beyond the special curves that we've talked about for things like maximums, minimums are. I might have you like graph it in your calculator, you know what I mean? I might have you graph it in your calculator, but I won't have you like totally analyzing a guy that's not one of your basic guys. And one of your basic guys, again, would be the, where are they? They're right here. The limacents, the roses, the circles, and the lemniscates. Those would be your basic guys. Did you have any questions about what to do, or was it just nasty and you're like, I really hope we don't see it tomorrow? Yeah. Is there anything else you guys need me to walk through? Evens or odds? Going once. Evens or odds going twice. Sold. Let's talk about that quest tomorrow. Sound good? And then I'll let you guys get working on the review, hopefully, so we can have a work day and bust it out and be able to ask each other questions, etc. So tomorrow we have a quest 25-pointer. We have a 25-pointer that is on sections 10.6, 10.7, and 10.8. What was section 10.6 on? It's been a while. We had spring break. It wasn't polar. It wasn't R's. It wasn't thetas. Yeah, I would go in your notes if I were you. Parametric had T's. And remember there was a mode in your calculator for T's as well? Parametric had T's, and there was a mode in your calculator for T's as well. Okay, with the T's, what could you be asked to do? With section 10.6, it's just been a while. If I were you, I'd be taking notes. With the T's, you could be asked to eliminate the parameter with T's or thetas. Wait, no, you just said parametric had T's. Yep, but didn't parametric sometimes have angles also? With sines and cosines? Eliminate the parameter. If you go to section 10.6 on the YouTube video, and if you watch me do examples on eliminating the parameter, you will see with T's and with thetas. Did we talk about how to get conic sections with parametric equations? Yes, we did. How to get circles, how to get ellipses. You might want to peek over that. how to get circles, how to get ellipses. We also talked about how to convert from rectangular to parametric or from parametric to rectangular. Aren't there some equations to help you go from a right triangle to either parametric, x equals y equals, or to go from function y equals and then get a t in there. There are some good examples for that also. Speaking of converting, we also talked about how to convert points. So if I already look over all those different ways of converting from rectangular to parametric and parametric to rectangular. Do we also have conversion-y things from section 10.7 as far as polar and rectangular? Yeah. We also have things from section 10.7 about converting from polar to rectangular and vice versa. So you have to keep a close eye on the question. Is it saying parametric or is it saying polar? There are equations for both, and actually all of them come back to a right triangle. What? All of them come back to a right triangle. All of them come back to a right triangle. If it was to go over an x and up a y, that's what we're used to get to an xy point. But guys, xy point besides going up. What's polar do? Out from the pole, yeah, but don't you have to turn an angle? So we have to turn a theta, and we have to go out an r. This triangle was a pretty important one for section 10.7 especially, yeah. The conversions in 10.7 were kind of like the key tricky types of problems that you guys faced. Like x squared plus y squared is r squared. Like x is equal to r cosine theta. Like y is equal to r sine theta. Like tangent of theta is y over x. Check the quadrant, check the picture. Okay, is that triangle important? Yep. You are going to have to sketch some polar points. But I was really nice and gave you one of those concentric circle-y graphs so you didn't have to stress about it. You're welcome. You're going to have to graph some polar points. And then, do you know how Kyle just asked about this 2 secant of theta in this section on section 10.8 that says to go ahead and identify the symmetry, the zeros, the max, and any other additional points? And I said, oh, I wouldn't give you a secant one. That's nasty. Guess what I am giving you, though? One of the normal ones. One of the ones that maybe has to do with like a limacon type of thing, or one that has to do with like a rosy type of thing. One of the normal ones. So even though I'm not giving you the secant one, the last long answer on the quest, is going to be of sketching the graph and identifying the key pieces of information. It's just not going to be a nasty like secant type problem. Yeah, Kyle. It won't be like the first 4. It won't be like the first 4. Those would just be circles. They're kind of, yeah. In some way, shape, or form. And guys, in graphing a polar curve, if I say something like, hey, show me a table, what do I mean? Choose nice theta, thetas and r's, plug in, get points, and always connect not with straight lines, but with curves. Yeah? Not with straight lines, but with curves. Now here's the dealio for tomorrow. The dealio for tomorrow is technically there is no problem on the quest that needs your calculator. Meaning, I've only given you unit circle-y things. However, there is one place at the very, very end where you would have to solve for cosine equals to something nasty. Like, it's not, but it's similar to, like 1/3. Is cosine ever 1/3 in the unit circle?
No.
Oh. Wouldn't you have to use second cosine and like do a weird degree-y thing that you don't know exactly what it is? Cosine inverse? Yeah. So we'll let you use your calculator tomorrow because of that one little baby thing at the very end of the quiz. However, on anything long answer, you know me by now. Will you be able just to give me a graph and be like, haha, I'm done? Or do you need to show me work? All right, cool. Have a good chunk of time, like 15, 16, 17 minutes to work on your review. Stay in your seats, but you can twist and collaborate with your groups if you would like. You have the review already written down, but I'm going to go ahead and pull it back up once again just in case you need it. If you don't have a book yet, go grab one really quickly. Oh, that's not you guys. That's not you guys at all. I'm sorry. Hold on. You're right here. Have your homework spirals ready to turn in tomorrow. Have your notes ready to turn in tomorrow. Have your phones up and in tomorrow. Let's get a good quest, okay? If you guys get stuck on something, let me know. Yeah. Okay. Yeah, Kathleen, I think it was just set equal to 0 and then solve with the unit circle. Let me go see. Oh, right here. There you go. Yeah. Is anybody stuck on anything? Okay. Jason, where's your calculator? At home. You're going to bring it for tomorrow? Okay. All right, book open. Remember, on reviews, you don't need to write directions. You don't need to give me all the problem details. You're just practicing. Okay? You get it okay, Kathleen? Here's the review, Jason, for you to write down. Well, sad thing is, you're really just using your calculator to find the graph, and then you're using your window to figure out where it falls. Now, betas are angles, so negative 20, 20 isn't like a normal angle range. I would usually start at 0 and 2 pi. Does that make sense? But when you got to something like, what was that weird one? This one, I think? Yeah. When you went to plug in that one of 3 sine. See how it doesn't seem to be done? So then I would go play, and if it's not 2 pi, I would try 4 pi. If it's not 4 pi, I'd try 6 pi. Just keep expanding. Except I do one more thing. I also change this to be the circle. Here's why. What if we had done what if we had accidentally gone too far? We would see the whole thing. We'd be like, oh, 0, 6 pi, no big deal. But we wouldn't notice it kept going. So that's why I like the circle, because then I know, oh, too far, too far. Let's go back to 4 pi. Yeah. You're welcome. Anybody else have any other questions from last night's homework I can answer? Or with your calculator?